Hi, everybody. My name is Keshav Raja. I joined COAPS as an assistant research scientist in April. Before that, I was doing a postdoc in the University of Southern Mississippi on near inertial waves. So that's the topic of my talk today, specifically wind-generated near inertial waves. Um, so why are we interested in near inertial waves? So we all probably know that to maintain the overturning circulations, the large scale flows in the ocean, we need deep ocean mixing. So it's generally thought of that most of the deep ocean mixing is contributed by motions that called internal waves. And then we also probably know that internal waves have two main sources of energy in the ocean, namely the barotropic tides and the wind. So barotropic tides can, when barotropic tides move over ocean topography, it can generate internal waves called internal tides. And that's one source of internal waves. This internal tides can propagate and then dissipate to contribute to deep ocean mixing. And another main source is the wind. So wind can generate ocean currents or it can power ocean currents and eddies, can generate surface waves, but it can also create internal waves called near inertial waves. And these near inertial waves, when they dissipate, it also contribute to deep ocean mixing. So lots of studies have been done on internal tides and surface waves, but it's only been recently that people are looking at global energetics of near inertial waves. So there are lots of uncertainty on how much power comes from wind to the near inertial waves and how and where do these near inertial waves propagate and dissipate. So this was the topic, the global energetics of near inertial waves was the topic of my postdoc research. Today, I'm going to talk about one specific aspect of it, which is something that I'm currently working on. So the main question that I want to ask is, how and where do these wind-generated near inertial waves dissipate in the global ocean? So to briefly summarize how these waves are generated, so whenever we have a storm track or a high frequency wind blowing over the ocean, it can have a resonant response on the upper ocean. So the ocean has a natural frequency, which is the Coriolis frequency, which is the rotation of Earth. And in that frequency, there can be a resonant response in the upper ocean. These responses have spatial variations, namely the convergence and divergence of these oscillations. And these convergences and divergences can pump energy through the mixed layer into the interior ocean, and then they can propagate as an internal wave in the near inertial frequency range. Thus, it's called near inertial waves. So in this figure, we see that the near Coriolis near inertial response transitions into a near inertial wave, and then propagates as high mode radiation or low mode propagation. So this mode refers to a vertical mode, which I'll explain in a few slides. So it roughly is a decomposition based on the horizontal scales. These modes are vertical normal modes. So low modes are generally associated with waves that propagate far distances horizontally, and high modes are waves that have low wave length, horizontal wavelength, and then it usually propagates not that far from where it is generated. Okay, so usually when we talk about waves, we look at the spectra to see where the frequencies are. So one important or one useful tool to study internal waves is to look at the rotary spectra, because especially near inertial waves have a rotary component. These are circular motions. So the rotary spectra is a way to decompose these vector fields into a clockwise or anti-clockwise component of motion. And when we do that, we get a figure like this. This is for the global ocean. These are zonally averaged rotary spectra of the surface velocity fields. And here we have the frequency in the x-axis. The negative frequencies correspond to the clockwise motions, and the positive correspond to the anti-clockwise motions. And then we know that the Coriolis frequency varies with the latitude, right? So the Coriolis frequency decreases from the poles towards the equator, where it's 0, and then continues growing in the southern hemisphere. And the color bar indicates the spectral density. So we know where the energy is. So if you look at the spectra for the whole ocean, we see that there is a peak in the inertial frequency region, and these are harmonics from the tidal forcing. So we have a diurnal tide and a semi-diurnal tide, and then we have harmonics of those as well. And then there is, of course, the mean flow here, and from the large scale motions close to the 0 frequency. So if we look at a cross section, like if you look at the rotary spectra at one point in a latitude, we see a figure like this, and we see that there's a peak close to the F frequency, which is the Coriolis frequency, and this is the near inertial peak. And these waves can propagate as any internal waves. It can propagate between these buoyancy frequency N and the Coriolis frequency F. So usually in oceans, N is less than F, and so these near inertial waves can propagate to regions where the F is less than the wave frequency. So if it's generated over here, it can propagate towards the equator, because F is lower in those latitudes. So that's the this is the definition of near inertial waves. We identify it using a peak in the rotary spectra in the clockwise component in the northern hemisphere, or anti-clockwise in the southern hemisphere. So when we isolate that near inertial frequency band and plot it as a global map, this is what we get. So what I'm showing here in color is the near inertial wind power input. So that's the power coming from wind towards the near inertial motions in the surface. And the vectors correspond to the depth integrated near inertial fluxes in the horizontal. And the data is taken from simulation, a high-com simulation with 4-kilometer horizontal resolution. And I had data for 1 month from May 20 to June 20. So we see that wherever there is wind input, it generates near inertial waves, and these waves propagate towards the equator. And the global integral of this wind input, so that the whole power coming from the wind to the near inertial motions for this particular month was 0.21 terawatts, and they propagate towards the equator as waves. So what we can do is to decompose these waves into modes to isolate different horizontal wavelengths. So the way we do that is using a Sturm-Liouville equation. So I'm not going to explain the maths behind it. So what it physically means is that we define a few vertical structure functions. So this is similar to how we decompose a vector field into normal basis, like x and y axis, for instance. We can define any orthonormal basis to decompose our vectors into. So we one of the normal bases can be horizontal eigenfunctions. Vertical eigenfunctions. The first five eigenfunctions is shown in this figure. So if we decompose this, decompose the vector fields into these eigenfunctions, the benefit is that we can isolate different horizontal scales of motions of near inertial waves. So for a given profile of stratification, we can calculate the vertical structure for it, and then we project the velocity and pressure fields onto these vertical structure functions to get the vertical modes. And then we can calculate the energy and the fluxes in each of these modes. So when we do that and then calculate the energy energy in each of these modes, we find a distribution like this. So the first 5 modes have almost equal distribution of the wind power input. However, the first 5 modes together correspond only to 30% of the total wind input. The first 5 modes of near inertial waves has almost equal distribution of energy as well. But the sum of the first 5 modes correspond only to the 62% of the total total energy. However, these first 5 modes almost captures all the horizontal propagation of the near inertial waves. So this is the total field, the one that I showed you before, and this is the sum of the first 5 modes of near inertial waves. So this corresponds very well. So we can see that the first 5 modes itself, or the modes can be as many as we can resolve in our model. The first 5 modes capture all the horizontal propagation of these near inertial waves. But it only accounts to 30% of the wind input on 62% of the energy. So if we propagate, so the reason why we are doing is that the first modes have the largest wavelengths. So these are the waves that propagate far distances from the source, from the place where it originated. If we plot the map of the first mode fluxes, we see something like this. So these are the large wavelength near inertial waves. So it propagates far distances into equator, towards the equator. So we see that for this particular month, most of the wind input happens in the southern hemisphere, and then it generates these large wavelength near inertial waves, and it propagates towards the equator. But what is interesting is that these waves do not reach the equator. It gets reflected or scattered in these ridges, the oceanic ridges. For this particular month, we particularly see this particular reflection, where a huge amount of near inertial waves get reflected this oceanic ridge. And this oceanic ridge is called Salasi-Gomez Ridge. It's off the coast of Chile. And then these waves cannot propagate further equatorwards. So this creates a kind of near inertial shadow on the equatorward side of these oceanic ridges. So this is a small video of what is happening in the Salasi-Gomez Ridge. So what I'm showing here is the near inertial wave kinetic energy, and it's shown for 30 days of simulation that I have. And we can see that the energy propagates towards the equator. This is equatorwards, towards the right. And then this is a cross-section of this ridge, and it gets reflected at this ridge, and the near inertial waves do not continue towards the equator. So it's getting reflected and then dissipate at this ridge. So we can define a local and remote dissipation of near inertial waves. The way I define local dissipation is by taking the wind input that goes to modes higher than 3. So the first 3 modes, I define it as low modes. So these modes these correspond to the near inertial waves that propagate far distances, and the rest of the wind input are associated with high mode near inertial waves, and they are assumed to be dissipating locally. That is, that they do not propagate far distances from where it is generated. So if we define a ratio like that, Q local, we find that Q local is more or less uniform throughout the global ocean. What this means is that most of the energy that is generated dissipate at the same location, and only a fraction propagates away from the source. And we can also similarly define Q remote, which is the fraction of dissipation that is not happening at the local site. And then we can get a map like this. So this clearly visualizes the contribution of near inertial dissipation coming from remotely generated near inertial waves. And we see that these are concentrated in the regions where there are oceanic ridges. These are submarine ridges over here, and the Mid-Atlantic Ridge and the Salazzi-Gomez Ridge. For this particular month, in May, June, most of the wind input is from the Southern Ocean, as I mentioned, and most of the remote dissipation of near inertial waves happen in these Salazzi-Gomez Ridge and in these ridges, and here as well. This is called Valves Ridge. So yeah, but if you look at a different month, so when it's winter in Northern Hemisphere, say for example in January, most of the wind input happens in the Northern Hemisphere, and we clearly see that the Mid-Atlantic Ridge completely blocks off all the near inertial waves generated in the Gulf Stream region, and we see that the remote dissipation fraction is higher in the North Atlantic Ridge and in the Hawaiian Ridge. So this is something that nobody has looked at before, and this is what I'm working on right now. So yeah, as a conclusion, you can say that low mode near inertial waves propagate long distances equatorwards, and they dissipate through topographic interactions. Whereas high mode near inertial waves, which are associated with internal waves with the low horizontal wave numbers, they dissipate locally. And for the month of simulation that I showed you, the Q local is around 80%, and Q remote is 0.2 in the global ocean, but it's very high close to mid-ocean ridges. So right now, what I'm working on is a 1 year of simulation with 8-kilometer resolution, so that I can resolve the first few modes and then define the remote dissipation fraction, Q remote of near inertial waves, and study the propagation and dissipation of these low mode near inertial waves and how much it contributes to deep ocean mixing. Thank you.